shows up everywhere in here. It's extremely important to understand the basic what's going on in the resonance. So what this refers to is the case where you have a system that oscillates, that's harmonic oscillations about some equilibrium point. There is some damping, as you always have, right? But then on top of that, you force the system. What does that mean? You force the system. What it means is that you don't let the system move by itself, but that you apply a periodic force. So letting it move by itself would be I displace it and let it go and watch it and measure the period and so on. Right? With resonance, what I'm doing is the system is going to do that, but on top of that, I'm applying a periodic force to it. So that's going to be this term. The periodicity of the force, I'm going to assume that the force is kind of continuously applied to it, and it's strong, and then negative, and then positive. The force keeps pushing on the system. Okay? It's positive, negative, and so on. Following this kind of pattern, this kind of function, dependent on power. So, what is the behavior that you observe for an oscillating system? So we can do that with this simulation. The magnitude of the applied force is F0, and I have it at the bottom of the screen. It's right now 0, there was no driving. And let's say that I put 2 for driving. So I'm going to keep B at 0.1. This omega here is the frequency of the driving force. And the other parameter that's important in the problem is the natural frequency, omega 0. So there's two frequencies, right? One is the frequency of the system when you let it go. You let it do its thing, it has some frequency, we call that natural frequency. But the other frequency is the frequency of the driving force. I don't have to apply the driving force at the same frequency as the natural frequency of the system. I can do whatever I want with the external force that I apply. So that frequency of the driving force is omega. It doesn't have to be the same as omega 0. I'm going to look at the case when I apply the driving force at the same frequency as the natural frequency. So omega matches the natural frequency of the simulation, which is 1.41. And I'm going to start this from equilibrium. So if there was no driving force, the object will not move. And then I apply the driving. So it's like starting with the pendulum at equilibrium, and I start pushing on it. Let's see what happens. So the location of the oscillator starts from 0. Goes up, starts doing oscillations. You can see the red line. Notice how the amplitude of those oscillations is getting bigger and bigger, as you can see in the bar. Same thing that happens when you're pushing on a kid in a swing. Exactly the same thing. You start pushing, and if you keep doing the same thing, applying the same force, the amplitude keeps growing and growing. You have to move back, right? So you don't get hit by the swing. You push, and go back a little because the amplitude is growing. Eventually, it settles into some stable behavior. And the reason why that happens is because of the damping. The damping is what's going to prevent the oscillator from gaining energy indefinitely. In the case of a swing with a child, you know that that's the case. At some point, you can push as hard as you can, and the amplitude of the oscillation of the child does not grow any more than that. It does depend on the damping that the swing will have. If there is no damping, really good swing, then you could get the child to go around like that. Right? But with good damping, you can push as hard as you can, and you won't make it go like that. So as you can see here, the motion of the object has settled into some periodic behavior. It follows the driving force, and the amplitude has settled in some stable value. So that was when the frequency of the driving force was matching the natural frequency of the system. Let's try a frequency that is below that. The behavior at the beginning is strange until it settles into a regular pattern. The solution, if you take the differential equation, there is the general solution has some part that doesn't last forever, it decays, and then there is a part that is stable. And that's the one that you end up having after a while. So once things get settled, the motion of the oscillator follows the applied force. So the frequency that matches very well the frequency of the applied force, of the external force that is doing the driving, and it's settled with some amplitude. You can see that this amplitude is smaller than the previous one. This amplitude is about 2. If you notice in the previous simulation, the amplitude was at 10. Now we can go to the other side, which is, what about I apply the driving force with a frequency that is bigger than the natural frequency? We said the natural frequency was 1.41, so I'm going to try 3 for omega. Once again, the amplitude should be smaller. You have a 10 to the minus 3 over there, times 500 is like 0 point something. So the amplitude is quite small. The oscillator reaches a stable solution, or behavior becomes stable. It follows the driving force, but the amplitude is small. So what's happening here, the behavior that you have of the amplitude as a function of the frequency is that when you hit the resonant frequency, the amplitude of the system shoots up. How much does it shoot up depends on the damping. The damping is what's going to keep things finite. So the more damping that you have, things look like this. When you hit the resonance, you see some noticeable increase in the frequency, but not so much. When you have less damping, it's very solid. If you apply any frequency that is not the resonant frequency, the system doesn't do much. But once you hit the resonant frequency, it goes wild, right? So let me see if I can show you that very quickly. That will be the last thing that we talked about. You have a problem about that. So what I have here is just a ring, metal ring. And when you hit it, it oscillates. It has a natural frequency of oscillation, which you can see when you disturb it. Now I'm going to apply, this is going to go up and down. So that's going to be the driving force, and I can change the frequency of the driving force. Okay, so notice what's going to happen to the oscillation. I'm going up in frequency. So I'm not changing the strength of the force with which this is moving. All I'm changing is the frequency. And you can tell that there's big oscillation. They actually have a very pretty pattern. The pattern is that you have one what we call antinode here, a node over there, another antinode up there, node here, antinode here. Okay. Does that remind you of anything you've seen or studied in some other? Correct. The orbit of the electrons around the nucleus of the atom shows that kind of pattern also.